know that feeling when you're talking to an AI, maybe trying to sort out a problem, and it just forgets everything you just told it, like 2 sentences ago? It's so frustrating, right? You feel like you're starting over every single time. Or maybe you've tried building an AI app yourself and hit that same wall. How do you make it remember things, adapt, maybe even play a game properly without just rewriting instructions constantly? Getting past those really rigid, one-shot prompts to build something truly dynamic, well, that's a huge challenge. So today, we are diving deep into exactly that. We're going to unpack a really key concept called modular-defined parameters. These are part of the CAFA protocol, and CAFA, pronounced like Kappa. It stands for the Cognitive Architecture for Flexible Agents Protocol. Our mission here is to really break down what these parameters are, how they function as the essential building blocks for AI that can actually remember and adapt, and why getting a handle on them is vital for anyone building or even just curious about more sophisticated AI agents. And our guide for this is an excellent lecture note from Associate Professor Jae-Wood Choi at George Washington University. He's also a principal investigator for the CAFA initiative itself.
Yeah, and what's really central here is that these parameters, these modular-defined parameters, they are essentially the tools that give an agent memory and adaptability. They're what let you move from like a simple static prompt to a much more flexible, stateful AI agent. If you want to go beyond just single questions and answers, if you want ongoing intelligent conversations or build complex apps, think games, tutors, this is really the starting point. It's the difference between, say, a snapshot and a whole movie.
Okay, that immediately clicks, thinking about those times AI doesn't remember. So let's get into how Professor Choi breaks these down in the CAFA protocol. You mentioned there are different types. What are they, and what's the fundamental difference?
Right. Good question. It's a really critical distinction. The lecture note lays out two main categories. First up, we have what are called system parameters. You can think of these as the system's own internal notes for a single turn of conversation. It's immediate scratch pad. They're reserved by the system. They're read-only, meaning the developer can't change them directly, and they automatically capture the state of that one interaction. So we're talking about things like the user's exact input for that turn, the AI's specific response, maybe even the system prompt that started it all. The notation uses things like @TUSHAG for the user's turn input, @TutorTag for the AI's response, and @TSTag for the system prompt. Their whole job is just managing the immediate context, the history of that specific turn, what just happened right now.
Okay, so system parameters are the here and now managers handling the immediate context of a single turn. Makes sense. So then these modular-defined parameters must be where the longer-term memory comes in, the persistence. Is that the secret sauce for making AI adaptable over time?
Exactly. That's where you build the more lasting intelligence. Modular-defined parameters, sometimes called agent parameters, are different because you, the developer, the modeler, create them. And the crucial thing, like you said, is they are not tied to just one turn. They're designed to hold data, maybe static data, like a list of options that doesn't change, or dynamic data that does change based on what happens. And this data can be used across the entire application, throughout many turns, even across different sessions sometimes. They really form that essential bridge, taking you from just writing isolated prompts to actually building a dynamic, stateful agent, one that can remember things, track progress, and change its behavior based on past interactions.
That sounds incredibly powerful. But let's push on the why a bit more. Why are they so fundamental? What's their main job in making an AI application, well, better, more robust?
Okay, so their primary function is really simple but powerful. They act as a named, reusable container for a list of values. Professor Choi's note used this great analogy. Think of your application like a workshop. Your data may be lists of services, questions, game rules are your tools. Instead of having those tools just scattered everywhere, making you search for the right one each time, you put them on a clearly labeled shelf. That shelf, that's your modular-defined parameter. So instead of writing the same list, say a list of fruit names, into 10 different prompts in your application, you store that list once in a parameter, give it a name like fruits. Then, whenever any part of your AI needs that list, it just refers to the fruit shelf. One single source of truth.
Ah, okay, I see the organizational win there immediately. No more scattered tools. But practically speaking, for someone actually building or maintaining one of these applications, how does that shelf system, this architecture, really help day to day? Because maintenance and updates can be a real headache.
You've absolutely hit on a core software principle. Don't repeat yourself, or DRY. It's vital for making applications that can scale and that you can actually manage without tearing your hair out. The source uses a perfect simple example. Imagine that fruits list. Let's say you need to add grape to it. If you use parameters correctly, you change it in one place. the @set command where you first define fruits. That's it. You don't have to hunt down every single prompt, every bit of logic that might use that list, and manually add grape. Think of the time saved. And, maybe more importantly, think of the errors avoided. It makes the whole application much easier to read, to understand, and crucially, to update safely as it evolves. It's really about building for change from the start.
That's a total game changer, yeah. Anyone who's stared at lines and lines of code trying to find every instance of something will appreciate that. Okay, so we've got the what and the why. Let's get to the how. How do we actually create one of these shells, one of these parameters? What's the specific command in CAFA?
Right. The command itself is @set. It's pretty straightforward syntactically. @set parameter value at s. When the system runs this command within a turn, and usually, yeah, you put this in an early turn, like turn 1, to set things up, when a session starts, it does two things. It creates a parameter with the name you give it, and it assigns the list of values you provide to that name. And the key is, once that @set command runs, that parameter and its list are stored in memory, available for all the turns that follow in that session, like writing on a whiteboard at the start of a meeting. Breaking down the syntax, parameter is just the unique name you choose. It's case sensitive, so fruits is different from fruits. And value is where your data goes. It's a string containing your list items, separated by the pipe symbol to note. So for our fruit example, the full command from the note is @set fruits, apple, banana, cherry, date, elderberry, @set. Run that, and boom, fruits exists in the agent's memory, holding that list, ready to be used.
Okay, @set creates the shelf and stocks it. Simple enough. So the shelf fruits is there, full of fruit. Now, how do we get things off the shelf? How does the AI access that data, maybe grab just one fruit or count them or something else?
Good question. CAFA gives you a really neat and flexible way to do this using square brackets on ENA. Let's assume our @set fruits command has already run. There are a few different ways or recipes to pull data out using these brackets. First, if you need one specific item based on its position in the list, you use @name and @set. So N is the position number. And this is super important. Indexing starts from 1, not 0, like in many programming languages, a common trip up. So if you write, say, the second fruit is @fruits2, @pay_bab, the system looks at the fruits list, finds the second item, and the output becomes the second fruit is banana. This is really useful for things like matching questions to answers or pulling data when you know exactly which position you need.
Got it. One-based indexing. Okay, noted. What if I don't want a specific one? Maybe I just need to know how many fruits are on the list. Or maybe I want the AI to pick one at random.
Yep, both are covered. To get the total number of items, you use @nameENA, that's a capital N inside the brackets. This just returns the count. So there are @fruits and @fruits in the list. Got a result in. There are 5 fruits in the list. The main use for this is often in controlling loops or other logic. You might tell a @repeat command to run @fruits and @times, ensuring it processes every fruit, for example. Like @repeat2, @fruits and would run turn 2 5 times. And for adding that bit of unpredictability or just variety, you can access a random element using @name. Add a period inside the brackets. Every time the system hits this, it picks one item randomly from the list. Great for making responses less robotic, for games, creative prompts, you name it. So your random fruit of the day is @fruits. It might output cherry one time, apple the next, elderberry after that. It keeps things fresh.
That random access seems perfect for personality. Okay, one more access method. What if I don't want just one item, but a part of the list? Like maybe the first 3 fruits or everything from the third fruit onwards. Can I grab a slice?
Absolutely. That's called accessing a sublist or a slice, and you use a :dot inside the brackets at namestart.end @cality. This pulls out a portion of the original list and gives you back a new, smaller list, still pipe separated. It's super useful for segmenting data like your easy hard quiz idea. The syntax is flexible too. At namestart.end, gets items from the start index up to and including the end index. So at fruits 2.4, grabs banana, cherry, and date, resulting in the string banana, cherry, date. You can also leave out one of the numbers at namestart. Gets everything from the start index to the very end of the list. Useful for, say, getting all remaining items. At fruits 3, give you cherry, date, elderberry, and the other way around. At name.end at outer gets everything from the beginning up to the end index. Perfect for top end scenarios. At fruits.3 results in apple, banana, cherry. You can see how powerful this slicing is. That quiz example is spot on. At questions.10 for easy mode, at questions 11. At fruit hard mode, all driven dynamically from one master list defined using @ and at fruit.
Wow, okay. Define once with @set, then access in all these ways: specific index, total count, random item, precise slices. That's incredibly versatile. But here's where it gets really interesting for me. The source mentions nesting these parameters. What does that actually mean, and what kind of, advanced logic does that enable?
Nesting is really where the magic happens for complex dynamic behavior. It simply means you can use the output of one parameter access as the input or argument for another command or parameter access. Think of it like functions calling other functions in programming. It lets you build logic that depends on the current state, which itself is stored in parameters, all without hard-coding values directly into your prompts. It allows for layers of dynamic computation.
Okay, layers of computation. That sounds powerful, but maybe a bit abstract. Can you walk us through a concrete example? That quiz game idea seems perfect. How would nesting work there?
Definitely. Let's use the dynamic quiz game example from the note. The goal is to have the AI automatically ask the right question based on the current round number, which can change. So first, in your setup turn, you initialize everything. You set your questions at set questions. What is 2 plus 2? What is the capital of France? What planet is third from the sun at MA. You set the corresponding answers at set answers for Paris Earth, and crucially, you set the starting round number, maybe round 2 for this example, at set, current round 2 at day. Okay, now later in the game, maybe the user says next question, and you want to display the question for the current round. Your prompt uses nesting like this. Welcome to round at current round at day. Your question is at questions at current round at S. See how at current round at is inside the square brackets for at questions. That's nesting. Now let's trace how the CAFA system figures this out. 1, it always resolves the innermost parameter first. So it looks at current round at, we set that to 2. So that part becomes the value 2. The expression now effectively reads, welcome to round 2. Your question is at questions 2 at 3. Now it resolves at questions 2 at DERS. It goes to the questions list and fetches the item at index 2. Remember, one-based indexing. That's what is the capital of France. So the final text shown to the user is, welcome to round 2. Your question is, what is the capital of France? And the beauty is, if the user answers correctly, you might have another command, update the state, say at set, current round 3 at HDUS. Then, the next time that same prompt structure is used, it will automatically fetch at question 3 without you changing the prompt itself. You're just changing the state, the current round value, and the nested logic adapts the output dynamically. It's incredibly efficient and powerful for building stateful applications.
That is seriously elegant. Just changing one variable, current round, changes the entire behavior.
Wow. Okay, so wrapping our heads around this deep dive into modeler-defined parameters, guided by Professor Choi's work in the CAFA protocol, really illuminates how we get beyond basic static AI responses. It shows the path to building agents that can actually remember context, track state over time, and feel genuinely dynamic and interactive. It's like giving the AI both a memory and a way to use it intelligently.
Precisely. Once you grasp these core concepts using etsat to define your data shelves, and then using the various bracket syntaxes and start.n to flexibly retrieve that data, plus the power of nesting, you really unlock the ability to create much more sophisticated agents. Agents that can pull content dynamically, personalize responses, run complex logic based on stored state. It makes your applications more robust, more engaging, and critically, so much easier to manage and scale. It truly is the difference between a simple script and an intelligent system capable of learning and adapting within a session.
So for everyone listening, maybe think about this. How does understanding these building blocks, these parameters, change how you view the AI tools you interact with every day? And if you're someone who builds things or wants to, what new possibilities does this idea of stateful dynamic agents unlock for you? What could you create now that seemed too complex before?